Hello. Next topic is storage bindings and lifetime. So the fundamental character of an imperative programming language is in large part determined by the design of the storage bindings for its variables. Okay, so most of the in the case of imperative programming languages, their characteristic is determined by how their variables or how the storage bindings are designed for their variables. So it is therefore important to have a clear understanding of these bindings. So the memory cell to which a variable is bound is that somehow must be taken from a pool of available memory. Okay, so when we declare a variable or when we use a variable, the memory cell to which a variable is bound somehow must be taken from a pool of available memory, and this process is called allocation. Okay, and we have a deallocation also. The deallocation is the process of placing a memory cell that has been unbound from a variable back into the pool of available memory. So when we do not need a particular variable any longer, then we can unbound that particular variable, and we can place or that memory cell allocated to that particular variable can be taken out and uh, push into this pool of available memory. Okay, so the lifetime of a variable is the time during which the variable is bound to a specific memory location. Okay, so we know what is meant by a binding. That is, we are allocating a memory cell to a variable. That is binding of this particular variable to a memory cell, and that is allocation. You can call it as an allocation. And when we assign a value to this variable, that is also a binding. Okay, and we have the lifetime available. Okay, and we can define lifetime of a variable, that is the time during which the variable is bound to a specific memory location. Okay, so the lifetime of a variable begins when it is bound to a specific cell, and this lifetime ends when it is unbound from that cell. Okay, so to investigate this storage bindings of variables, it is convenient to separate scalar variables into four categories according to their lifetimes. And these categories are, so we are trying to talk about storage bindings of variables, and we are trying to separate scalar variables into four categories. And these are very important: static, stack dynamic, explicit heap dynamic, and implicit heap dynamic. Okay, and they have some all these have some advantages and disadvantages. So first we will look at the static variables. What is meant by static variable? Okay, so static variables are those that are bound to memory cells before program execution begins and remain bound to those same memory cells until the program execution terminates. So when we write a program and when we compile this, okay, so we get an executable code, and this program starts when we run that particular program, that starts its execution. Okay, so the static allocation means this static variables will be bound to this memory cells before the program execution starts. Okay, and another important thing is that those will remain bound to those same memory cells until program execution terminates. Okay, that is known as static variables. They're statically bound to some memory locations. So statically bound variables have several valuable applications in programming. Okay, so globally accessible variables are often used throughout the execution of a program, thus making it necessary to have them bound to the same storage during that execution. So suppose we are using some variables as globally accessible. Okay, so which means they will be used throughout the execution of a program. So we can have them bound to the same storage during that execution. Okay, when the execution begins till the execution ends, they will have the same binding to some storage. Okay, so sometimes it is convenient to have subprograms that are history sensitive. Okay, such a subprogram must have local static variables. Depending upon their history, the subprogram's state can change. So in that case, this subprogram must have a local static variables. Okay, so these static variables will have a lifetime within that subprogram only. Okay, outside the subprogram, they will not be alive. So one advantage of static variables is efficiency. That is, all addressing of this static variables can be direct. Okay. Other kinds of variables often require indirect addressing, and which is very slower. Also, no runtime overhead is incurred for allocation and deallocation of static variables, although this time is often negligible. Okay, so we have allocate this. We'll allocate this memory cell, and even before their execution starts. So no runtime overhead is incurred for allocation and deallocation of static variables. Although that is allocation and deallocation time is very negligible, that overhead will not be there in the case of static binding. Okay, in the case of static variables. So one disadvantage of static binding to storage is reduced flexibility. So in particular, a language that has only static variables cannot support recursive subprograms. This is a problem with the static binding, because if it is statically bound, they will be bound to the same memory cell. So when they are bound to the same memory cell, they can hold a single value only. Okay, so we cannot have recursive subprograms. In a recursive subprogram means when we have multiple activations of this, we have multiple activations of the same subprogram simultaneously. Okay, and which means a different activation will have different values for this variables. But if we have a statically bound variables, then they cannot have because they are bound to the same memory cell till end of this program execution. They cannot have multiple values, because in different activations of the subprograms they can have multiple or different values, but that is not possible with the case of static bind. And another disadvantage is that storage cannot be shared among variables. For example, suppose a program has two subprograms, both of which require large arrays. Okay, and suppose that the two subprograms are never active at the same time. Okay, and if the arrays are static, they cannot share the same storage for their arrays. Okay, so we have two subprograms. Suppose we have a program and that has two subprograms, and both require large arrays. We have subprogram 1 and subprogram 2. They require large arrays. Suppose these two subprograms are not active simultaneously. So which means it is possible that if we have if we have one array, that particular array can be shared among these two subprograms. But if the arrays are static, then they cannot be shared among or they cannot share the same storage. If they have the same storage, then they have the same value will be there. So a second subprogram cannot alter that. Okay, that is a problem with static bind. Okay, and C++ allow programmers to include the static specifier on a variable definition in a function, making the variables it defines static. Okay, in C or C++ languages, we need to explicitly define it as static. Okay, so we can use static keyword to declare it as or define that particular variable as static. Note that when the static modifier appears in the declaration of a variable in a class definition in C++, Java and C#, it also implies that the variable is a class variable rather than an instance variable, because that is static. So they will have different instances will have the same value for that particular variables. Okay, so when we have static modifier, in the declaration of variable in a class definition, it implies that the variable is a class variable. Okay, and class variables are created statically sometime before the class is first instantiated. Okay, so these class variables will be created statically, so their values cannot be changed, and sometime before the class is first instantiated. So when the class is first instantiated, or when the first instance of this class is created, at that time itself these class variables will be created. Then we have stacked dynamic variables. The next type is stacked dynamic variables. So stacked dynamic variables are those whose storage bindings are created when their declaration statements are elaborated, but whose types are statically bound. Okay, they're stacked dynamic, which means their storage bindings are created when their declaration statements are elaborated, but whose types are statically bound. Okay, their storage bindings will be uh, they are created when the declaration statements are elaborated. Okay, but their types are statically bound. Okay, so elaboration of such a declaration refers to the storage allocation and the binding process indicated by the declaration, which takes place when execution reaches the code to which the declaration is attached. Okay, that time when the execution reaches the code to which the declaration is attached, the storage allocation and the binding process will happen. Okay, but their types will be statically bound. So we can say elaboration occurs during runtime. Okay, so for example, the variable declarations that appear at the beginning of a Java method are elaborated when the method is called, and the variables defined by those declarations are deallocated when the method completes its execution. Okay, so we have, suppose we have variable declarations that appear at the beginning of a Java method. They are elaborated. What is meant by that elaboration? We have the storage allocation and the binding process. They are known as elaboration. So when the method is called and the variables defined by those declarations are deallocated and the method completes. So when we call, or at the beginning of this method, all these particular declarations are elaborated, and when the method completes its execution, they will be deallocated. Okay. So as their name indicates, stack dynamic variables are allocated from the runtime stack. Okay, so they will be allocated from the runtime stack. So some languages, for example, C and C++ allow C++ and Java allow variable declarations to occur anywhere a statement can appear. Okay, so in C++ and Java we can have variable declarations anywhere a statement can appear, we can have a variable declarations also. So in some implementations of these languages, all the stack dynamic variables declared in a function or method may be bound to storage at the beginning of execution of the function or method, even though the declarations of some of these variables do not appear at the beginning. Okay, so in some implementations of these languages, we all of the stack dynamic variables declared in a function or in a method, and this not including those declared in nested blocks. We exclude the case of nested blocks, but these variables declared may be bound to storage at the beginning of execution of the function or method, even though the declarations of some of these variables do not appear at the beginning. Okay, they will be because the problem with this kind of language is that these variable declarations can appear anywhere in the program. Okay, so even though the declarations of some of these variables do not appear at the beginning, we can have this variables declared in a function method, and that will be bound to storage at the beginning of execution of the function itself. Okay, so in such cases, the variable becomes visible at the declaration, but the storage binding occurs when the function or method begins execution. Okay, so that is the difference. So the variable becomes visible at the declaration, but the storage binding, that is, and its initialization, if it is specified in the declaration, this will be occurred when the function or method begins execution. Okay, the fact that storage binding of a variable takes place before it becomes visible does not affect the semantics of the language. Okay, so here the fact is that the storage binding of a variable takes place before it becomes visible. So when the variable becomes visible at the declaration. Declaration can be anywhere in the program, but what we say is that the storage binding occurs when the function or method begins its execution. Okay, but there that is visible somewhere when they are declared, and that declaration is possible anywhere in the program. Okay, that is a difference. So that, but even though that is the case, it does not affect the semantics of the language. And the advantage of stack dynamic variables are that to be useful, at least in most cases, recursive subprograms require some form of dynamic local storage so that each active copy of the recursive subprogram has its own version of the local variables. Okay, that is the main advantage of stack dynamic variables. We can have recursion possible. Okay, and these needs are conveniently met by stack dynamic variables. Even in the absence of recursion, having stack dynamic local storage for subprograms is not without merit. Okay, because all subprograms share the same memory space for their local variables. Okay, so even without this recursion, having stack dynamic local storage for subprograms have some merit. That is, all subprograms share the same memory space for their locals. That is the advantage with stack dynamic, because all this space is taken from the runtime stack. And the disadvantage related to static variables of stack dynamic variables are the runtime overhead of allocation and deallocation. Okay, possibly slower accesses because indirect addressing is required, and the fact that subprogram cannot be history sensitive. Okay, so in this case, the subprograms cannot be history sensitive, and we have the time overhead of allocation deallocation, and that will slower accesses. And here we are using indirect addressing. So we have a variable and we have uh, this address of this variable. It is not that case. We are using indirect addressing methods. Okay, so we have some memory address for this particular um, memory location, and then we'll have some offset. Okay, so based on that, we'll have address of this particular variable. So the time required to allocate and deallocate stack dynamic variables is not significant, because all of the stack dynamic variables that are declared at the beginning of a subprogram are allocated and deallocated together rather than by separate operations. Okay, so when we have beginning of a subprogram or end of a subprogram, these stack dynamic variables are declared at the beginning of a subprogram, are allocated and deallocated together. Okay, so we do not require separate operation for that. And Fortran 95 plus languages allows implementers to use stack dynamic variables for their locals. And we have explicit heap dynamic variables. So explicit heap dynamic variables are nameless or abstract memory cells that are allocated and deallocated by explicit runtime instructions. Okay, that is written by the programmer. So these variables which are allocated from and deallocated to the heap can only be referenced through pointer or reference variables. Okay, so these instructions, these explicit heap dynamic variables, um, are nameless memory cells, and these are allocated and deallocated by explicit runtime instructions written by the programmer. We'll see some examples also. And these variables which are allocated from and deallocated to the heap can only be referenced through pointer or reference variables. Okay, so we can use pointer or reference variables to refer these variables that are allocated or deallocated to the heap. The heap is a collection of storage cells whose organization is highly disorganized because of the unpredictability of its use. Heap means you have a continuous memory cell and you can block of cell. You can use this heap for storing your variables, and you can use maybe in the upper part of the heap or lower part or in the middle part. This stack or heap organization is, or you can say that organization is completely disorganized. So you can use in the case of stack you have a format. Okay, so you should use the first cell, then second cell, etc., or in queue, or in other data structures. But in the case of heap, this organization is completely disorganized. So the pointer or reference variable that is used to access an explicit heap dynamic variable is created as any other scalar variable. Okay. So an explicit heap dynamic variable is created by either an operator, for example in C++, or a call to a system subprogram provided for that purpose. Okay, so maybe we'll use in the case of languages like C++, this variable is created by an operator, or we'll have some system subprogram and we'll call that system subprogram provided for that purpose. Okay, and that is the case with C language. Okay, maybe you are familiar with the operator new in C++. That is an allocation operator. That's what we said. These heap dynamic variables can be created by an operator. Okay, new is an operator that uses a type name as its operand. When executed, an explicit heap dynamic variable of the operand type is created and its address is returned. Okay. Because an explicit heap dynamic variable is bound to a type at compile time, that binding is static. So this explicit heap dynamic variable is bound to a type at compile time, and that binding is because it is happened during compilation time. The binding is static. However, such variables are bound to storage at the time they are created, which is during runtime. These variables will be created uh, during runtime, and that time they will be bound to storage. So in addition to a subprogram or operator for creating explicit heap dynamic variables, some languages use a subprogram or operator for explicitly destroying them. Okay, some language also uses includes a subprogram or operator for explicitly destroying this heap dynamic variables. As an example of explicit heap dynamic variables, consider int C++ code int star in node that creates a pointer of type integer, and that pointer is known as in node. Okay, then in node equal to new int. So here new is an operator. Okay, so that will create explicit heap dynamic variable of the type integer. Okay, create a heap dynamic variable. Then delete in node means that will deallocate the heap dynamic variable to which the in node points. So in this example, an explicit heap dynamic variable of int type is created by the new operator, and this variable can then be referenced through the pointer in node because that is the name given to that. Later the variable is deallocated by the delete operator. So C++ requires the explicit deallocation operator delete because it does not use implicit storage reclamation such as a garbage collection. Okay, in the case of C languages we have this facility, but in the case of C++ that requires explicit deallocation operator delete. And we have the third type is implicit heap dynamic variables. Implicit heap dynamic variables are bound to heap storage only when they are assigned values. Okay, so in fact, all their attributes are bound every time they are assigned. Okay, for example, consider the following JavaScript statement: highs, that is equal to 74, 84, 86, 90, 71. So regardless of whether the variable named highs was previously used in the program or what it was used for, it is now an array of 5 numeric values. Okay, that is implicit heap dynamic variable. So the advantage of such variables is that they have the highest degree of flexibility, allowing high generic code to be written because we can directly use it, and when they are declared at a particular statement, there these variables, regardless of their previous declarations in the program, if any, or what it was used for, it is now of that particular type declared just now in the current statement. Okay, so one disadvantage of, so that is a high, we can say that it has highest degree of flexibility. Okay, so one disadvantage of implicit heap dynamic variables is the runtime overhead of maintaining all the dynamic attributes, which could include array subscript types and ranges among others. Okay, so we should have this overhead, that is a runtime overhead, that we should maintain all the dynamic attributes which could include array subscript types and ranges. Another disadvantage is the loss of some error detection by the compiler. Okay, so because of this repeated declarations of the same variables, there is a chance that some error detection can be lost by the compiler. Okay, compiler may fail to detect some errors. Okay, and these are the basic types of variables. These are the 4 basic types of variables. Okay, thank you.